So the next type of error that we're going to discuss is what's called the alternating series error bound. This is actually a special case of the next error type, the Lagrange remainder. But it is sometimes asked about by name on the AP exam, so I am treating it a little bit separately. So alternating series are series where the terms that are being added together are alternating signs, so plus, minus, plus, minus, plus, minus. So it has to be an alternating, the terms have to have alternating signs. Then, if we look at the absolute values of those individual terms that are being added together, those terms need to decrease as we go towards an infinite number of terms, and they have to approach zero. And I need both of those. So we need alternating series, the absolute value of the terms decreases and approach zero as we go out to an infinite number of terms. If we have all three of those, then we can bound the error. Bounding means that we're just saying, hey, the absolute value of my error is less than a certain value, or alternatively, the error is somewhere between this. This is actually something you're used to when you hear people say, like, for example, polling, that, oh, these polls are accurate plus or minus 5 percentage points. Its error has been bounded as the absolute value of the error is less than 5 percentage points. Oops. This should be a less than or equal to. My apologies. Not a less than. That's a less than or equal to. So to bound it, if it's an alternating series, where the absolute value of the terms decreases and approach zero as we go out to an infinite number of terms, the absolute value of the error is less than or equal to the absolute value of the next term we would have used. And again, an example makes this much easier to demonstrate. So we're going to start by writing the third degree Maclaurin polynomial for sine of x. Well, this is one of those Maclaurin series that we need to memorize. So the Maclaurin series for sine of x is, we're going from 0 to infinity. It's -1 to the n. Sine is an odd function, so I want to use x to the 2n plus 1 over 2n plus 1 factorial, because it's odd powers and odd factorial. So third degree means I'm going out until I hit the third power. So if n is 0, that's a positive x to the first over 1 factorial, which is x. If n is 1, it's a negative x to the third over 3 factorial. And actually, that's where I stop. If I kept it going, like in my series, I'd have x to the first over x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus, and so on. So approximating the sine of 1/2, I plug 1/2 in for x. And I can leave it unsimplified like that, or if I simplify that, that'd be about 0.479. So there's my third degree Taylor polynomial. Here's my estimate of the sine of 1/2. And then I'm told to use the alternating series error bound to estimate the error of my approximation. So first thing I need to check, is this an alternating series? Yes, it is. I can see plus, minus, plus, minus, plus, minus. If I ignore the alternating parts, is x to the 2n plus 1 over 2n plus 1 factorial decreasing as n is going towards infinity? Well, if you remember, factorials grow faster than polynomials. So my bottom is getting larger faster than the top is. So it is decreasing. And that allows me to say that the limit as n goes to infinity of x to the 2n plus 1 over 2n plus 1 factorial is also approaching 0. So I'm allowed to do the alternating series error bound, which means that the absolute value of my error is going to be less than or equal to the absolute value of the next term I would use. Well, I use the first two terms, so the rest is my error. But because it's alternating and the terms are decreasing and approaching 0, the maximum error is this first term of the error. So of the x to the 5th over 5 factorial. But I used a 0.5 for x, so the absolute value of my error is less than or equal to the absolute value of 0.5 to the 5th over 5 factorial, which I could leave it like this. But for those who like to simplify, that means the absolute value of my error is less than or equal to 0.00026. So we can actually see the Maclaurin polynomial is very powerful for us in that with just using two terms, we get a really good estimate for the sine of 0.5.